Today I will show you some different forms of columns, and I will introduce some different forms and assumptions and some of the transfer columns, some types of high strength concrete. First of all, try to introduce some different forms of column. For example, these are typical columns we see nowadays. If we see the column is too long, you can need to imagine there's have a chance to have a buckle, and that means the capacity should be reduced. And then if you see the super tall building, you normally see the so-called super columns. And nowadays the architect will think about different forms of column. They try to use a steel wall. It's a hanger steel wall. And in the past you can see there's a tube-in-tube buildings. There are many columns outside of the buildings, and the A-frame and the V-shaped form and the incline form and the diagram form and the tree branch. And you can see another form of the column is tries to make a little bit mesh, and that means you can imagine actually they can form certain types of truss, and another form of mesh. And you can think about this is for example, if this is a one-story building, think about use one columns or many columns as possible, and then you can see the outcome is something like this. You can see this is many columns formed by one-story building, but the outlook is very special. And other type of building is some kinds of twisting, and you can imagine the columns can be twisted like the outlook of the form. And another assumption you need to understand is there's two common assumptions. The first one, to assume the column just take the vertical load, and then due to the less loading we produce it, and the size would be less. And this cannot be easily seen. It can easily seen for the super tall building. For example, sometimes you want to reduce the size in certain locations, you can use this assumption. Another assumption is commonly used for the typical forms of building. The columns take all the loadings, vertical load and lateral loads. That means the wind loading, and the size should be larger. For example, this is a steel building. Normally the steel building assumption is the central core take all the lateral forces, and you can imagine the columns just take the vertical loading, and you can see the final outcome is the column size should be less than the typical one we see nowadays. Another form is when you go to Mont Court, you can see, for example, architect want to let the middle columns to the size should be less, and how can we do it for the engineers? They can think about using the assumption of just take the vertical loading and assume that the bigger columns can take all the loadings, and you can imagine this is the final outcome, and the end user may be very happy about only have a very small column in the middle. And sometimes you can think about is a V-shaped form. Okay, the V-shaped form, the special thing is the top chord. In certain stances we can take the tension forces, and sometimes we take the compression force. That means to make the building become equilibrium or stable, try to maintain a top chord. And other term is a torsion. For example, if all the loading combine together and add to the center points of the core wall or columns, that means no additional forces. In another location or in other cases, certain buildings will not have a central core. Sometimes the core will offset a little bit. You can see them. That means, like the cases in here, they can reduce the additional forces that we call it. This is the torsional forces. That means the building is twisting. Another thing is the trigonal frame. And other theory is the first one I want to introduce is you need to remember if something is a cause, it means it's a voice. What is the columns loading taken? The column just take the cell waste loading and the beam loading. Because there's no more slab, that means no more loading. You can imagine the loading for the CC should be less. For example, for the CA, there's a concrete slab. Using the bi-area method, you can imagine half the loading they were taken by the CA, another half by the CA. That means you can see the blue color. For the CB, half of the column grid line will be taken to the CB, and half of the grid line will be taken to the CB. The CB area should be larger, and then you can imagine the loading taken should be larger. This here show you some of the column loading taken. Remember, the vertical load at the bottom should be the larger ones. Okay, that means you can imagine the bottom size should be larger. On the top one, we only take the roof. You can imagine the size should be less. That means there's two types of trimmed types forms. For example, if we want to reduce the size from the middle, we can do something like this. Sometimes the architect want to in line, they will offset to the left or to the right. You can see the size reduced like this one or the left one. This is show you some bending moment diagram. Remember, try to think about changing the location of the column. It's not an easy task. For example, like this one, we need to provide a 2-story steel truss to ensure all the loading will be transferred to the another column. So you can imagine maybe this is about 8 meters. You can imagine we need to have a 2-story structure to make sure all the loading can be transferred from the top to the bottom. This is one kind of common incline column. You will see the most special thing is you need to understand sometimes the top one should be take the compression forces. That means the steel beam or concrete beam, we need to provide compression forces. Another, the bottom one should take the tension forces. This is final output of the V-shaped column. You can see many common nowadays. And this is some steel truss made by concrete, not the steel. Okay. Remember, if you do the steel columns, we need to have a fire space, fire protection board, or the concrete to make sure there's a fire protection for the steel one. Sometimes you can think about how can we reduce the size of the column. The first one, we use the high strength concrete. The second one, we use the composite columns, like this one. Try to put the steel section inside the concrete columns. And the third one is try to think about is put the outside column is a steel. This is some of the example. For example, you use the concrete string is 70 and concrete string is 45. You can see the size should be smaller for the higher strength. That means when you see this simple formula, you can see the first term is based on the concrete string, and the second one is based on the steel reinforcement. The third one is due to the steel section we provided. That means if I want to reduce the size of the column, try to think about increase the concrete string, or increase the steel reinforcement, or increase the steel section provided. And this is show you one of the example. Normally the graph is when the compression force is dominant by the compression. That means as a point A, and point B is the moment is larger. That means if certain cases, if the loading we provide within this envelope, that means the capacity of the column is good enough to take the loading. This is a World Trade Center. In the past, we want to reduce the size of the columns. We try to provide more columns we provided. This is one of the tube-in-tube we provided. Another new form is a tension bar we provided. And the third one is a tree branch. Okay, you can see many new buildings nowadays, they try to do it like this, a little bit different, and the central core wall system. And this is a so-called fair face column. You can imagine what they did is just take out the formula after concreting. This is the final outcome. The architect don't put too much on the column. That means they can do the final outcomes of the concreting. This is so-called the feature they want to provide. And remember, column is very important. If someone want to remove it or try to trim it, you need to consult the structural engineers. Otherwise, you can see the so-called fatal errors for this accident. The building collapsed in Hong Kong. Thank you.